Can you see the screen? Hello.
Yes, sir.
Okay. Okay. What we were discussing in the last class was the algorithmic approach to solve the data access synchronization problem. And uh, what we found in all the four attempts, the first, the second, third, and the fourth, we found that instead of taking any additional help from the operating system or from the hardware architecture or from the compiler itself, uh, merely by using the logic, we would our objective was ensure that the access to the shared resources are is consistent, or it will not lead to anomaly in some sense, in some other sense, that if multiple processes try to access that shared resource, that need to be ensured, or that will be ensured in a mutual exclusive fashion. The progress property of one process will not be hampered or dictated by other existing processes who are trying to compete, and at the same time there will be no deadlocks or live locks. And we found that it was to the it was using Peterson's algorithm, one can ensure it, and we used two additional shared one shared array of flag and another shared variable turn to ensure that. Okay. And that we found that it is free from deadlock or live lock, and it also guarantees mutual exclusion. Now extending, but the point that we noted is verifying that these properties are satisfied might be tricky in this situation. So another approach that Lamport took, in fact, is Peterson's algorithm may be generalized for a number of processes, but we took a we'll take a different case of using Lamport's algorithm, Lamport's Bakery algorithm, to try a solution for n number of processes, for multiple processes. Okay. So here the idea is there will be not just two process P0, P1, but there will be a pool of processes P0 up to n minus 1 or P1 to n. There will be n number of processes. And these processes will not assume anything special about their execution, just merely using some logical steps. We would like to ensure that access to the shared resource through the by these processes will be consistent. So what Lamport took, so this will be one major topic of today's class, discussing about Lamport's Bakery algorithm, and then we'll switch to uh, the case of creation of shared memory. Okay, so what are the exact functions through which we can create those shared memories, that will explain, and that will be the end of today's class. So this Bakery's Lamport's Bakery algorithm, the key idea was it was inspired from the way order is ensured out of chaos in the bakery shops or the ice cream stores or the motor vehicle servicing. So what it actually we can think of, say this is the shop, and say this is the counter where from they actually get their products, and there are vendors who come. Okay. And those vendors come with those vehicles, and there are multiple vendors which come for those for getting the products, like this, and some are just waiting and having this ready, like this. So that's a typical situation, and they are not interested in forming a queue also. That's the case. So they are just roaming here and there, and this is a counter where they are supposed to get from, I mean, they will pay and they will get their products, and which they will sell outside. So that's the case. So in such a scenario, the only thing that you can assume, or I mean, that is quite fair to assume, that these say total there are at this moment 5 vendors or customers, as you can say. So they are having some IDs. Okay, so this is maybe the customer 1, this is customer 1, this is customer 2, sorry, this is 1, this is 2, this is 3, this is 4, and this is 5, or maybe this is number 8. And 5, 6, 7, they have not yet arrived, like that. So let us assume that they are total n equals to 8 number of customers, and 5 of them are at present, they are present. Okay, and they are having some unique IDs. That is fine. But then it may happen that this 3 came first, or arrived first, then arrived 4, then arrived 8, like this. So their order of arrival is not dependent on their IDs. They may arrive in any certain order, and that order need to be preserved when they seek the service. That is the point. So the only thing that you can, and this vending shop or this store is not capable of having a monitoring mechanism. So these vendors are fair enough, or they are well behaved in the sense that when they come, they will try to acquire a token. Token means a particular token number or token ID. And this token ID, they try their level best to get a unique token ID. Okay, so maybe that this one, so who came first? So this person came first. So the token ID, maybe it is say T1, and this is say T2, and this is say T3, and this is say T4 and T5. So in this situation, if vendor 6 and 7 they arrive, so how to get the token ID? The next token ID, what should be the what should be their logic? So the idea is these new persons who just arrived, they will try to acquire a token, and that token, what they need to do? What is the last token value? Highest token value? Hello?
7.
No, highest token value right now. The tokens.
So 5,
It is
P5.
5, right? Yes, 5. So what do you expect? 6 and 7. What should they consider to be their token?
So 6 and 7.
6 and 7. Now the thing is, generally what we do when there is no queue, you suddenly arrive in a scenario where it should be ensured first come first serve. So you keep on asking people. So are you the last person? Are you the last person, like that? And then whoever says no, I am not the last. So yes, he is the last person, like that. So you basically poll the existing persons if they are not from the queue, and you to figure out that who is the last person. So in this case, a similar polling can take place. The new incoming vendors, they can ask the existing ones and figure out that what is the last token value, the highest token value. Now the highest token value seems to be here, it is 5. So this says that okay, my token value will be 6. So like that. So this is say 6 identifies that its token value will be 6. What about 7? So can 7 guarantee under this situation that it will also acquire the same token, a token value 6 or 7? There is no coordination as such. A new person comes, it polls the existing vendors and finds out the last token value, implements that, and assigns its own token value to be that. So does this process guarantee that both 6 and 7 will acquire unique values like that 6 or T6 and T7? Hello? Can you guarantee that 6 will get T6 and 7 will get T7? or maybe
No, sir.
or maybe 6 gets T7 and 7 gets T6. That is also fine with us, right? Because they arrived in the same time. So if we follow this process, so it might happen that if they arrive simultaneously, they receive a token ID which may be different from the existing ones, one more than that, but they get the same token, they grab the same token value. That might happen, right? Hello? So they may get the same token value T6 and T6. So if this happens, how to break the tie? So if all others are served, so for others what they will do? So whenever you find that this is free, so you will try so the existing customers will try to find out whether I am having the so the next token I am having the next token, so you will go and get the service and leave. Once he leaves, the next person knows that okay, now 5 is getting served, so my turn is 6, like that. So when if each and everybody got served and their turn comes, there is a tie because they both got the same token. So how to break the tie in this case? What can be the simple case of breaking the tie? What is the other hello? So both the persons came with acquired or grabbed the same token value. So how to break the tie when their turn comes?
So unique ID.
Okay, so that can be one simple case because it is guaranteed that they have registered for this shop and they are having some unique ID, right? So we can think of that they are having the some unique ID. So in case there is a tie, so the one who is having the lowest ID will be given the chance first. So that is, so at least this protocol they all follow and they are well behaved to this extent. But the only thing is they don't want to form a queue, and there is no as such physical queue that gets formed. That is the case. Okay, so this is the simple logic that follows, and that is how out of uh, one can make the system can create an order out of chaos. And so they all just follow the same rule and there is no monitoring, manual monitoring of who gets, and there is no absolutely no chaos. So the thing is we try to see that whether this same logic or the same scenario can be embedded or can be encoded in solving this data access synchronization problem where multiple processes can compete. Okay, so let us write the equivalent form, the equivalent code form. So here what we assume that each customer, in this case, the equivalent of customer is a process in our case. So a process is a customer, is having a unique ID, and we know that it is already there. Every process is identified by a unique ID based on its creation time and all. I mean, and uh, one entry, each customer. So sorry, on entry, each customer or process receives a token number. Now we don't say that this token number is always going to be unique. If you have got simultaneous entries, they might end up with same token numbers, and the customer with the lowest token number is served next, okay, from the existing pool. And there is no guarantee, as I mentioned, that the multiple customers or processes do get the same token numbers because of this process, because there is no single authority that who actually allocates tokens. Rather, the customers poll the existing customers who are having a non-zero token or who are in that particular area, and finds out the maximum token value, increments it to 1 and assigns it to be its own token. So in such a case, the one with the lowest ID is served first, and if C1 and C2, Ci and Cj receive the same token number, and then if I is less than j, that is ID, whoever's ID is less will be served first. That is the rule. Okay. So let us see that if we try to implement this in practice, then what happens? I mean, in case of a process. So here is a shared resource R, and okay. So how to store the tokens corresponding to n number of processes? Now the number of processes are finite, so we say that we are, in this case we are dealing with say 7 or 8 8 customers, so number of processes are known. So corresponding to each process to store its token, so the token values should be maintained corresponding to each process. So the thing is, this shared number, this number, or you can consider it to be the token, so this is where it stores the token values. So there is an entry corresponding to each process in that pool, or who are basically competing for R. and initially it is set to 0 because nobody has acquired a token. So 0 means that particular process has not acquired a token. So once it acquires a token, it should be at least 1 or 2, some non-zero value. And once a particular process completes its execution, it releases the critical section, it will reset its token. Okay, so here the token, a non-zero token, essentially means you are setting your willingness that you are competing for the resource, or you are trying to enter into the critical section to access that particular shared resource. Okay, so once you are done, you should reset your token. So you basically said that I am not willing, kind of thing. But instead of just setting it to true and false, you basically store a number that will uh, dictate that when your turn will come and how many processes are ahead of you, like that. So here this is, you can see that this is a code that will be executed by process pi. So this is basically I. In fact, this code, the similar logic will be executed by all the processes in number of processes. So p0, p1, p2, each and every process will basically follow the same code, exactly same code, and that is basically I mean, these are differentiated by the value of I, that's id. Okay, so this is this while loop. Should have put this. So this is the while loop. So it is trying to get into the critical section multiple times. So this part is there. So what are the steps? What are the steps? The first step is you should get the token. So before you access the critical section, you should first get the token or acquire the token. Once you have acquired the token, now this is the process. So this process is check for other processes if it's need, if the current process, which is the process we are talking about. This is the ith process. This is the ith process's code. So the ith process first gets the token to be filled up in number I, and then it will try to check all the remaining processes, n number of processes, and what is the condition for waiting? It cannot jump on and try to access the critical section, provided it finds that, what is the condition? It has to wait if other process, some other process, jth process, has a non-zero token value, token with value less than the ith process, right? That is a simple case. So even if my PID is 1, if I find that uh, PID 2 or 3, the processes with PID 2 and 3 are having token values lesser than this, then I have to wait till their turn is over. Or if I find that when j is less than, so if I find that the j, so I is checking for all the j processes. So if I find that there is some other process j which is having the same token value, if the token value is less, I have to wait. If the token values are same, then I have to find out whether my PID, that is I, is greater than j. Then also I have to wait. So this is a waiting condition. So the waiting condition says that if a process, so the ith process will wait if some other process j is having a non-zero token value which is less than that, or it has got the same token value but the id of the j is or the value of the j is less than I. Is that part fine? Hello, are you getting the point? Hello.
Yes, sir.
So this for loop actually keeps you at, so you one by, so this is iterative loop, so you basically check the first process, second process, third process, like this serially you have to check. So once you are over, so you don't have to you have no check waiting for any of the process existing processes. That means it is now your turn and you get access to the CSR. So can you write the piece of code to be executed here? I mean, this get token means what exactly I need to write here to get the token, to grab the token? Can you just specify that? So get token means I am trying to write what number, who is executing this process pi. So I want to get the token value corresponding to the ith process. So ith process wants to get, so what value it will, it will set here? Number I should be what? What will be
So,
number I?
maximum of number plus 1.
Maximum of number, say 0 comma number 1. I mean, I'm just writing in a very naive form. Number 2, how many numbers will be there? How many numbers need to check? Yeah, if I have
I
started from
minus
0,
1.
it will be n minus 1, right? So you check all these numbers. So you basically find out the maximum of all this, add 1 to it, right? Simple logic. So once it's done, you start doing this. So there is a waiting logic. So wait for this. So how I encode this? What is the if condition for this? I mean, this is so what is basically the condition that I have to write here? What is the condition? First of all, you have to check that. So who is checking? Who is executing this for loop? The process I is checking. And then whom it is comparing with? It is the jth process. So first thing is what it should check. What it should check, if number, if the jth process has acquired a number, right? If this is equal to non-zero, this is the first case. If the jth process has not acquired any token, that means it is not willing. So there is no point that no question that the process I need to wait for that particular process, right? So this is the first condition. This, if this is the case, and what I need to write, the simple case where the process J has acquired a token, but the token value is less than that of process I. What should I write? Number,
Number j is less than number I.
number I. So this is the simple case. There is no tie. So if this is true, if this condition, if the J has acquired some token, then I have to also check that the token value is less than the number I, or what can be the other case? What can be the other case?
Sir, equal number, but process ID
So
is greater.
number J is equal to number I, and so or this, and J is, so I'm putting the waiting condition. So what should I write? How J is connected related to I? J is lesser or greater than I? Which one?
Less than I, sir.
Less than I. Then what I need to do? I have to wait. So this is the condition. So I have to keep waiting. So this is the condition. How should I write it? It is not if. I have to keep waiting like this. So this is a while condition. So this whole condition ensures or uh, determines whether I need to I get stuck while scanning through all the existing processes or all the existing customers. I get stuck at the jth customer itself. So this means no matter what the others, ideally don't know whether I have to wait for j plus 1, j plus 2, but at jth point, or the at the jth particular customer, I find that I have to just wait. Now if I find that the process I skips all the while loops for all the j's, that means what? I am here, so I am free to use the critical section. Is that fine? Is that okay? And finally I have to release the token. So what is the release token? What should be the statement there?
Number I is equal to 0.
Number I is set to 0. So now after that, if I leave and if some other process comes, a new process comes, he will never check. I mean, even though he checks, he will never need to wait for me because I'm not interested, I'm not willing. Okay, so I'm out of contention or out of this competition of accessing the R. So this is what it means, right? So this is what we discussed. Now tell me that if this solution is correct or not. Do you all agree that this is correct? Is this a correct solution? Okay, I've already shared the slides, even though there are some hints, but just tell me that you may have gone through it. That's not a point. But tell me that if is it a correct solution? Does it ensure that everything is correct? It seems to be everything is correct, right? We considered the tie case. We considered everything else. So is this correct? Hello. What do you think?
Need to consider this maximum value of integers also.
A bit louder.
Do we need to consider the maximum values of integer also?
Yeah, okay, that can be ignored. Let us assume that, that is a relevant point, but let us assume that that will not be a problem. So it will not exceed that limit. Say, for example, are there other issues that uh, gets into the problem, like the synchronization issue? Like, will it ensure mutual exclusion? That's a basic point. Does it ensure mutual exclusion? I got your point. You say that each time it will enter and it will grab a token, so that number of tokens will definitely it can take the maximum integer value, and if you keep on entering like that, so it need to wrap up, right? So let us assume that that is not the problem. So it will not be exhausting the token numbers that are available. Will mutual exclusion be guaranteed? Say this is the case. Say we have got P0, say P1, P2, P3, P4, right? Four processes. And say, for example, that's P1 and P2, they are not competing for this right now. And it is P3 and P4 who are competing, who wants to get the token value and wants to access it. So nobody is there in the arena. So P3 and P4, unfortunately, they come simultaneously. And what happens? P3, P3, what it does, it starts scanning, and P4 also starts scanning. So what they will find? The max value, because nobody is there. So what is the max value they will find?
0, sir.
It will be 0, because P3 will be scanning P4 and P4 will be scanning P3. So both, none of them has acquired a token. So they will scan basically max of this will return 0, right? It will be returning 0. Now say, let us assume that P3, say P3, so it will get 0 plus 1. So, so it is basically 1. It has computed the token value 1. But before it can write it back to number, it has been preempted, right? See the situation. So P3 got this calculation correct. This part is done, but it cannot write it back. So before, so it just computed, but it has not been able to, you know, write it here in that particular. So this P3, it is still 0. This is still 0, but it has computed it to be 1, and has been preempted. Now P4 comes, and P4 does the same thing. So I can ignore all the rest. So it is all 0. P4 also computes it to be 1, right? So this is possible. We know that this is possible. Now P4 is not preempted. So P4 writes it here. So P4 makes it 1. Okay. And then P4 comes to this for loop, because let us assume that it is still having enough time, say for example, and P4 comes here, and P4 skips P0 and P1 and P2, because they are all 0. This is this condition, and it finds that what it finds, number j is less than number I. So is that correct? What it will find, P1, P2. In case of P3, what P4 will find? I am talking about process P4. So P4 computed, stored its value, and came to this for loop, and it will be checking this while loop one by one, scanning through the processes. So P4 will check P0 to be 1, P0 to be 0, P1 to be 0, and P2, sorry, P1, P2, P3 all to be 0, right? So will it get stuck in some while loop? Are you getting my point?
No, sir. It will use the resource.
So it will come in the CSR, and it has, say, it has started accessing CSR, right? Critical section. whatever it wants to do, it is there. Now suddenly it got preempted, because this, when you have designed this solution, as we mentioned that we never assume that while you are in the critical section you cannot be interrupted, there cannot be timer interrupt, so anything can happen. So the thing is, while it was p4 was in uh, so we say that p4 is in the csr. Okay, so while it was in the csr, it got preempted, and p3 was already preempted at this point. Now once it got preempted, now p3 got scheduled. So what is the first thing that we will do? What is the first thing that p3 will do?
Make it one, sir.
Write
Number
the
I.
token value in its number, so it will make it 1 now. Now tell me what is going to happen. Now p3 starts checking the for loop, right? In the for loop, what it will find, it will skip this, it will skip this, and it will come to itself. When it comes to itself, what it will find, it will not definitely check, it will not wait for itself, because it is so that you can write a trivial code. So pc is not going to wait for itself. Now it comes to p4. So when it comes to p4, what it finds,
Sir, its
when
PID
it
is
comes
less
to
than
p4,
P4.
first thing is there is a type. So first thing is p4 has got a token, first thing. So it has got a non-zero token, this is fine. And it finds that these numbers are same, it's not that it has got a lesser, so both numbers are same, and this p3 is less than p4, so 3 is less than 4. So what it should decide, p3 will decide, will p3 wait?
No, sir.
Are everybody are you getting the point? Will p3 wait now?
No, sir.
No, sir.
p3 will not, and p3 also. So eventually what will happen, p3 enters critical section. So now what happened, the whole process, the whole exercise was to ensure that mutual exclusion is guaranteed. Now will it guarantee mutual exclusion?
No, sir.
So now this again the problem here. So the whole effort is going to be in vain. So what is the point that we should add or modify to make sure that this ensures mutual exclusion by simple modification? So what we miss here? What is the key logic that we miss here? So this is what we have, what I have just now explained. So it says that now the situation is both P3 and P4 enters the critical section simultaneously, and the mutual exclusion property is violated, right? So how to ensure it? What is the minimal change that you should make? Can you give any clue?
Sir, just after assigning token, it should go to sleep.
Just after assigning token?
Yes, sir. We make sure that all the waiting processes are assigned token first.
So you should rather say it in a different way, that whenever I am acquiring a token, see the point, whenever I am acquiring a token, in the process of acquiring a token, process of acquiring means not only computation and writing it back, this is the whole process, right? So during this process, if some other process is checking my status and trying to decide whether it needs to wait or not, it should not do that, right?
Yes, sir.
All it says, say if p3 or p4, say p4 is now checking the while loop in the for, so if p4 is in the for loop and checking for this while condition corresponding to p3 or some other process, and it should ensure that this p3 is not in a process of acquiring. If it is not interested, it's fine, but if it is in a process of acquiring, this might lead to a clash. So the logic that it should change is, when you are in a process of acquiring, that means this step need to be, so before and after this step you have to do something. You have to you have to say that I'm in a, so I'm in a choosing process, now I have chosen and now I'm releasing the lock. So it's something kind of how do you flag it? If you look back to this example, so if both of them are trying to acquire the token like this with their vending machine, if both of are trying to do this, so you may raise your hand like this. Okay, you may raise your hand, so both will raise their hands. So they are trying to flag or signal others that if you are checking, so when I'm raising my left hand means I'm just counting and trying to get my token and write it in my maybe uh, on my vending machine. So when I'm doing this process, you should not so you should better wait instead of taking your decision whether to skip me or not, right? So this raising the left hand is something. So when you are in a process of doing that, you raise your left hand, and when you are done acquire the token, you just again put it down. How to ensure it here? So for that, maybe we have to use another array which will basically act as a flag shared. Maybe this is just whether I am choosing or not. It is just like a boolean. It's not an integer. It's rather a boolean array of n elements, right? And it should be initialized to false because initially none of them are actually in a process of choosing. Is that fine? So if this is the case, what should be the statement here? What will be the equivalent of raising your hand and putting it down next? What is this? Raising hand
Choosing I
means
is equal
what?
to true.
Choosing I equals to
Is it true, sir?
true, and once you are done choosing, the I equals to false, right? So once this is there, so what change you need to make in this for loop to make this effect? That you cannot, so for the process J whom you are right now interested in, before you check this condition whether you have to wait or not, you have to make sure that process is not in a that particular jth process is not choosing the token. So what you should write? So here is another loop, another waiting loop, busy loop. What is that? You have to check what? The choosing value of
I J.
choosing value of j, because I is check doing it. So I should uh, if the choosing of j is true, then I need to
Wait.
wait. That
While.
means why? That's all. So again there is a busy waiting. If jth process is is uh, is choosing its token, it's acquiring its token, right? So if I just make this change, do you think that the problem is solved? Have you got the problem? If I make this change, that means any process, this is its own token choosing process, and this is its it's checking of whether it need to wait for others, and if it is not to wait, it will go for the CSR. So this is I am going to acquire the token. You raise your hand, left hand, and you put it down. Meanwhile, others who are executing and trying to check whether you have got a token less than or greater than, they should wait if you are in a process of waiting. J also will have to wait for I, and I also have to wait for J, like that. And the rest of the process is the same. So do you think that it is done now? Is there any other problem that can arise? Are you getting me? Hello? Can you think that if this is now correct or not? How we could have avoided the previous problem that we illustrated, like this P3 and P4 case? So if I just incorporated this solution, then P3, so when this P4 was executing, you see P4 was P4 computed this, and before P4 enters, so P4 would have got stuck to P3, right? After P4 has computed, can P4 continue with the critical section in the previous example? Simply P4 would have got stuck at this point because it knows that P3 is in the process of choosing, it has not chosen. So what happened actually, P3 executed this choosing true, it got the token, and it has not even written this. So this P3's choosing flag is still true, right? So P3 got stuck, preempted at this point. So P3's choosing flag is still true. So P4 could not have skipped that step, the while step, and could not have entered the CSR in the previous example. Are you convinced with that? Hello?
Yes, sir.
And whenever P3 finishes, like, so definitely it will there will be a timer expiry, and then because it's a busy waiting, so P4 waits, and whenever this preempted, P3 comes, gets its chance, P3 will commit this modification in the number 3, and then it will make it false, and it will do, maybe it got preempted after that. Now if it has been preempted after that, then P4, if it is scheduled again, it was earlier waiting in this choosing loop while choosing, and it finds now P3 has acquired. Now when it executes this while loop, it finds that P3 should be given the priority because it has got a lower, because both has got the same token number, but the P3 has got a lower ID. So definitely in this example, if we have made this modification, P3 will be getting the chance before P4 gets into the CSR, right? So if multiple processes arrive in the arena simultaneously and they somehow acquire the same token value, it is guaranteed that they will be getting access to the critical section according to the order of their IDs. The lower ID will get the first chance. That is guaranteed. And if that is guaranteed, then we can say that mutual exclusion is guaranteed, because first of all you are getting a unique token, then there is no problem. Lower token value will given the chance first. If you are getting a tie, then by all means the lower PID value with the same token number will be given the first priority, and there is no point, there is no possibility that this such situation will be violated. Okay, so this Lamport's bakery algorithm, it's easier to verify whether the conditions are satisfied, and there is no deadlock because and there is no live lock also, because a simple case that we assume in the assumptions itself, that once a process enters into the critical section, it is going to release it uh, within a finite time. So definitely your turn will come after a certain time, and there is no live lock, there is no deadlock. So there is a strict ordering that has been proposed by the algorithm itself. So that was why this Lamport's bakery algorithm has been used or has been studied in a or multiple process solution in an algorithmic approach, and that is a very nice elegant solution. And in fact, Lamport contributed in many ways in designing other distributed algorithms or other algorithms in operating system. Okay, so like Dijkstra, Lamport also has a lot of contribution in solving those classical problems. So this is one of them. Okay, so this guarantees mutual exclusion, progress property, deadlock. So now we'll look into some of the Linux system calls, and we'll try to see the examples in the next class. Okay, so how execution works. So another 5-10 minutes, so I'll just talk about this. So shared memory in Linux. So till now what we are writing as shared int x, or say shared int a10. So what are these? So this means, so this array or this particular variable is a kind of it's a unique kind of resource which may be used by multiple processes which are no way dependent on each other. This can be a parent child, this can be multiple childs created by the parent, or this can be any other processes which don't have any relation in the parent child hierarchy. Okay, so this is something like say during those Arohon or during the other kind of events, what we find that, say we have got the CCA, we have got the GLAG, and there are other clubs also like the dance club and then other uh, motor clubs and all this. So what we know that the authority asks you to create shared resources and you can share it accordingly. So say for example CCA is having a much larger group, and they have got various more activities than the others, if it is so. So they are trying to create in the oval, or maybe in some other So they are trying to create a particular arena, right? So this is they are creating, and once they are creating, they are allowing other clubs to say this is dance club or whatever. So they are allowing other clubs also to use it. So they are going to use it. The other clubs also going to use it. But who is going to create it? So CC is going to create it. So they will monitor the creation and they will make this possible. So the thing is, but the CCA they are they are having their in their own area. They are having other events. They are also having their own area. They are having other events. The dance club also having that. So they are given some space in the institute to carry on their activities. Now this is a common. So during the uh, annual event, they are having a common resource which they are going to share. Definitely, there should not be any clash, but there that is other case. Now let us look into the case that how this shared resource will be a part of the other the different clubs which are in some sense independent of each other's activities. They have got the different bodies or the different rules and all. So they are in some sense completely independent and they are trying to create, and who is going to create? So some of the clubs, say for example CCA is going to create. So once it is created, it wants to attach this particular resource to itself, and it also allows others to also use the same resource attached to them. So what can be the probable steps to do this? What can be the first step? First step is to create, right? So forget about the function first. So first is to create. So create means what? So somebody needs to create. So it may happen that GLAG creates, or maybe the dance club creates. Let us assume that CCA creates. So when you try to create something, now you can think of there are two IDs that is considered. So one is a global ID. So global ID is, say global ID says that this is arena. Global ID means the global name. So this is arena that they decide to use. So CC knows that is arena, dance club and GLAG also knows that is arena. So when it creates, so this creation of the space is not a part of the first thing is you should know that this is not a part of the CCA's own office space or own space or none of this club. So this is in a completely different location. Now once created, creation does not mean that CCA can just use it. What is the next step that it wants, that it needs to have access to that? So create means the facility has been just created, but still this arena is not yet a part of CCA. So what is the other function that it requires? To attach it. So this is literally it is called attach, right? So this attach means in some sense you try to connect to this. So this gets connected to it, or I mean this something like this. So you can think of that this becomes a part of its. So this is the CCA space earlier, and this becomes a part of it. This is what attaching means. Now, if the GLAG wants to do the same, what do you expect? What the GLAG should do? First of all, once it attaches, then it can organize programs and events and all this. It's is as normal as that. And once it is done, it will call detach to just detach it, right? And this detachment does not mean it will be destroyed. So destroy means maybe after 7 days, after a week time, the whole thing will be packed up and it will be cleaned and all this. So that is called it's a destroy. So attach and detach means, attach means you make it a part of it, and detach means you just dissociate with yourself. Okay. So if GLAG wants to use the same facility right now, what it should call? What it should call?
Attach.
Yes, but if it calls attach, so what it should attach? So how it will identify that particular global resource? It's a global resource. How it will associate or how it will identify that?
Sir, the global ID.
Yes, that is possible, but the way things are done here, and this is also it makes more sense probably that arena. So arena, who has given the name? You say that okay, CCA created and CCA named it as arena. Now GLAG says that no, we don't want to use the same name. We would like to our naming convention is something different. So we say that this is a we say that this is room one, okay, and this dance club says that this is floor one. So dance floor, this is floor one, this is room one. or say Gila says it's hall 1 or room 1, something like that. Okay, and CCA wants to call it as something like say space 1 or whatever. So the point is the global ID, the global identifier or global name is arena, but each of the different processes or each of the different clubs may be willing to use a name or a naming convention that is more convenient to them. So they would like to, so when they are attaching, they are trying to create this name, or I mean, it's not attaching. So during the creation, they are trying to get this name, okay, this name of this local ID. So this is a local ID, this is a local ID like this. So if they have local ID, so the things, this is a global resource, but the CCA will always identify it as space 1. The dance club will identify it as floor 1, and the GNU club will identify it as hall 1 or whatever. Okay. So the point is these Chilag and dance clubs, so both has to call the same create and attach, and if they are done with detach like this. So just merely attaching will not work. You have to again call the same protocol of create, attach, detach. But when it calls create, so the protocol is the same. It finds that it has already been created. So whether you need to create it, if it is already created, you don't create it actually. But in the process, what you get, you basically get the local ID. Okay. So the idea is any process that wants to use a shared resource must call the create function or create system call, then it should attach it. Attach it means it's a logical connection to the club space. So you can think that the club will have a much larger space to work. And detach means you basically disconnect it. Maybe it is a payment basis. So if you are attaching or connecting to it, you have to pay. So the clubs need to pay per hour basis like that. So you basically, once it is done, you detach it. Again, you attach it like that. So that why it is done, because there are less clashes and you can have a consistent way of using it. What is destroy means? So who is going to destroy it? Who is going to destroy it? Hello?
Everyone.
No, just see, once the arena is once the event is over, so do you think that all the clubs need to destroy it one by one? Just
But
the
create.
physical creation is once and the destruction is also once. Okay, you may say that, okay, why should I take the charge? So maybe whoever has created it, they should take the responsibility. But here the case is maybe the CC has created it, but the GNU log is taking the charge of destroying it. That is fine. But only one particular process destroys it. That's fine, and anybody can destroy. So the thing is, this first tree is must be there in all the processes, but this destroy is optional. Maybe that you destroy, and once you destroy, the thing is you have to make sure that others are not using it still, right? So that need to be somehow ensured. And if it is destroyed, you cannot see. So the thing is, so this is a kind of this shared resource. There are ways to know that it has been created. So before I get into that, so let us see that how it works. So I've got another 5 minutes of time. So you see, so these functions, so to create, you have got SHM get. So get means you are basically getting means you are trying to create a shared resource. SHM AT is basically attaching it's the attach function, and DT is for detach function. It's easy to recall also. And SHM CTL is for controlling. So destruction is you are trying to do something. So it's like trying to get control over it. So you can say this, check the status, and this SHM CTL is used basically to destroy. Okay, so there is no other additional function. Now this SHM get, what it accepts is a global key. Okay, and this is the size. So how much, what should be the size of the stage or whatever. So you should specify the size, and this flag is trying to specify that what is the mode of this shared. So will it be 666 in case of a process? That means will it be a read access, write access, execute access, or it will be just like read access to others and like that. So whoever is the creator process can specify the access permissions to this shared resource, and this is quite valid, right? So what you can try is you can make a particular shared resource accessible and modifiable for you, but for others it is just readable. So CCA can make modifications, but GNULAG and dance clubs, they can just use it and they should leave the arena, that's all. So they don't have the permissions to modify it. That is possible. So those access permissions. And SHM-AT, so what you get here, so this SHM-GET will provide you the local ID, will return you local ID will, so you pass on the global ID, and global ID need to be known by all, and the local ID you receive, and when you attach, you just attach, so this local ID you pass, and this is the address which you try to connect it to, and this is the flags. Okay, if it is successful, it will return a non-zero value, otherwise not. And this detach will basically, you just give the local ID here. If you give the local ID here, it will be detached, that's all. There is no more options required. Okay, and when you destroy means again you specify through your local ID, you specify, and then there are some other uh, uh, say fields we'll see later. Okay, so there are just two codes. I'll not run these codes, I'll run the codes in the next class. So as you can see here, say this is the process, say this is the process who is the creator, process which creates, and this is the process which just uses it. Okay, so as you can see here, we have included the ipc.h, shm.h, and this types.h. And what it does here, this is, what is this shm key, what is this, this is a global ID, right? And as you can see here, this global ID is set, is hard coded in both the processes, because that you need to know. So in your common meeting, you have decided, okay, we'll call it as arena, like that. Okay, so now here you can see that shm get, it is calling shm get with the shm key, that means the global key it is passing, then it is passing the size. So what it is actually allocating here is an array of two elements, integer array of two elements. Okay, so this is what it is passing, so 2 into size of int. Can you see this? Is it visible? Hello?
Yes, sir.
Okay, and here you can see that this is the access permissions, and this is or IPC create. So this or is very important. So if you give here or, so that means if it is not been created, it will create it. If it has been created, it will just get the local ID. So this is a local ID. Okay, if you don't give it, if you say here, if you don't give it, so it will just assume that it has been created, and if it has been not done so, then it will give an error message. What the point? So if you want both, any of the two processes to have the creation facility, the responsibility to create, you should write here or IPC create. But if you don't write it, if you just write C666, it is expected that the process, before it starts execution, the shared resource has been created, it is already there. Got the point? But this access permissions mode need to be there. Now what is the next part? SHM-AT that we mentioned. So this local ID, we are putting it here. This is null, we can ignore it right now, and this is 0. So what we get here is, what it returns is, you see this is shared memory. So this is a integer, this is a void pointer. So this void pointer is actually pointing to the shared. So so this is the shared segment, say for example, shared segment, shared page segment. Okay, and this is this process's own space, and this shared memory, so this one is here, shared memory. So this will basically point to this. So that is how you are attaching. So you are attaching this shared piece to your own virtual space. It's a virtual address space of this process I. This is a process I, say for example. Okay, and so this shared memory is basically, so now once it is done, then because you want to, it's void type, so you can so this will be like this. So you can typecast it to integer and you can assign it to x and you can modify and update. So once it is done, as you can see here, you are free to write and read from that location using a normal assignment operator. So as if you have just used it, you have just dynamically allocated the space. So during dynamic allocation it was from the heap, but in this case it is from a shared segment which you have prior created, or you have created and you are trying to use it. So once it is done, you see it is as simple as that. So x0 x1, what is this x0 x1? This is this location and this location, and what are those? Those are in a shared page segment. Okay, and after that it just detaches HHMDT, and what it does, so sorry, I just modified it in the code and I have not reflected it here. So it's a shared memory, so the same ID if you pass, it will be detached, but this process is creating but it is not destroying it. So this is the process, say J, which when it creates when it calls SHMGT, it may give this, it may not give this. So it will get its own SHM ID. It will get its own local ID. So it's local ID, and that local ID in this attach mode, in its own virtual address space of J, it will have another some X here. So this X will be pointing to this one. Okay. So this process, so this X is points to this one. This process to this shared memory or whatever variable name, it will point to this one. So both are capable of pointing to the same location, and that is how they are shared. Okay, and then you can typecast and you can use it. So we are just reading. So in this process we are writing some values, and in this process we are reading the values. They are just reading, you see. So whatever has been written in this process on this shared piece will be read by this process J, and after doing that it is detached. So this share so all, so these all has been messed up. So this SHM ID, so it will be detached. Okay, and then SHM CTL, it will be the destroy function. RM means removal. So you give that particular flag, it will be destroyed. So the process to actually detaches, destroys the shared memory and exits. And hopefully that let us hope that before this is executed, this process gets completed. So it is up to you, your responsibility to make sure that before some of the process or any of the competing process, before it executes SHM CTL, all the other processes has detached it. Otherwise nobody knows what is going to happen. They will get some error message. So they will get some error message when they try to access it. So it is up to you to ensure it. So what I mean to say is this process I can create and merely attach and detach, and this process J which can, and this process J can connect it, attach, detach, and as well as destroy. So it is not necessary the process which actually physically creates need to physically destroy the resource. Okay, so in the next class we'll look into the code. I'll run the code and see that how you can see the status and how you can see the IDs that got created from the command line. So there's a command called IPCS. Uh, so status you can check all the shared memory that has been created. Okay, so this much for this class. So in the next class I'll show within 5-10 minutes the examples of this, how it gets actually created, and we'll see that the modifications are done, and then we'll start the semaphores. So one request is I would like to take a class today from 4 to 5 instead of extending this class, and I would like to complete the whole syllabus by next week. So is that possible? Because in any case Animesh his syllabus is almost completed. Can I take a class today from 4 to 5? Hello?